this class, let us now continue with the equations that we started developing in the last lecture. We started developing equations for the three-phase induction machine. We began with equations like VA equals VAS equals RS into IAS plus P times psi AS. We had 6 such equations like this, and then subsequently we expanded expressions for psi AS in terms of IAS, which is the phase current flowing through the phase A, as well as the other currents IBS, ICS, and then the 3 currents in the rotor and so on. And we saw how the first row of that expression will look like. Similarly, one has to fill up all the other 5 rows of the system description. We can attempt to write these equations in a simplified notational form, where we write V as the vector. Let me underline that to denote that it is a vector, equals R matrix, which is the resistance matrix, multiplied by the current vector multiplied by P times, that is d by dt of an inductance matrix multiplied by the I vector. This is a simplified notational form of the equation, where the matrix R is a square matrix. Remember, each row of this describes an equation in the like this, and let us now write these different vectors and matrices. So you have RS and then 0 0 0 0 0. That means this corresponds to the AS phase, and then BS, CS, AR, BR and CR, and being a balanced machine, these first 3 rows would then look like this. The next 3 rows correspond to the resistance of the rotor, the equations of the rotor, and therefore they would be RR and 0, and again 0 0 0 RR 0 RR. So this would be the resistance matrix. This is multiplied by the vector I, which means IAS, IBS, ICS, IAR, IBR, ICR. So you get RR into IAR for the first row, RS into IAS, RS into IBS for the second row, and so on. The inductance matrix, which is L, could be written as L11, M12, M12 transpose and L22, where each is a small submatrix by itself, where we can write L11 as LLS plus LMS. This is the leakage inductance per phase, and this is the magnetizing inductance, and then this is the mutual inductance between the stator phases, MS again, and here there is MS, LLS plus MS plus LMS, and this is MS, MS here, LLS plus LMS. This is the self inductance matrix. So if you write the I vector here, this matrix is going to multiply the vector corresponding to IAS, IBS and ICS. So one can call this as the self inductance matrix of the stator. L22 is then similarly described. This pertains to the inductances of the rotor, and therefore what you would have is LLR plus LMR, and then MR, MR, MR here, again LLR plus LMR, MR, LLR plus LMR. So this is the matrix that is going to multiply IAR, IBR and ICR, and the form is very similar to that of this matrix. M12 on the other hand describes the mutual flux linkage between the rotor currents and the stator flux. At this point it is between the rotor flux caused due to stator currents, and therefore M12 is going to describe mutual inductance behavior, and that we had seen the first row yesterday, I mean the last class. So that is MSR into cos of theta r, and then you have MSR into cos of theta r minus 2 pi by 3 MSR cos of theta r plus 2 pi by 3, and then you have MSR cos of theta r plus 2 pi by 3 MSR cos of theta r, that is MSR cos of theta r minus 2 pi by 3. This would be MSR cos of theta r plus minus 2 pi by 3 MSR cos theta r plus 2 pi by 3, and that is MSR cos of theta r. So this is the form that the M12 submatrix is going to take, and what occurs here is the transpose of this M12 matrix, because whatever term comes here would come in the first column and so on. So one can write down this elaborate description of the induction machine, where, as what we had seen earlier, the stator phase axis are AS, BS and CS. This describes the spatial orientation of the stator axis, and the rotor axis are displaced from the stator axis by an angle theta r, that is the rotor axis, and this angle is theta r, and therefore you have BR here and CR here. So all these angles are theta r. So this is how the machine description would look like. This is called as the natural reference frame description of the induction machine, natural reference frame. That means the variables that are associated with it, that is the variables I and V, are the naturally occurring variables in the induction machine. This is, for example, the actual voltage applied to the stator A phase, and this is the actual flow of current in the stator A phase. Similarly, in the rotor equation you would have the actual voltage applied to the rotor and currents flowing in the rotor and so on. So since they are the natural variables, it is then called as the natural reference frame description. As before, this is the electrical aspect of the induction machine, that is the electrical subsystem of the induction machine, which then says if you are going to apply a voltage VAS or VBS, VCS and so on, how much current would flow. But in order to arrive at that, you need to know what is the angle that is involved, and the angle will in turn depend upon where the rotor is and therefore how the rotor is going to move. Therefore, in order to complete the description, you need to describe the mechanical subsystem as well, and the link between the electrical subsystem and the mechanical subsystem is provided by the torque that is generated, and therefore you need an expression for the torque. Torque, as we have seen earlier, can be described as half of I transpose dl by d theta into I, where L is the matrix L as is given here. Now, if you evaluate this expression, it will come to a fairly long lengthy expression. One can do that if it is required, but as of now we do not need that expression, we will proceed further. This expression for the torque is then for what is called as a two-pole induction machine, two-pole machine. The expressions we have so far obtained, all these expressions assume implicitly that the stator magnetic field and the rotor magnetic field are two pole fields. If you remember, we had described the induction machine stator like this, assume it is a circular stator, and then we had the A phase of the stator here and the return conductors here, and then you had the next phase which was here, and then the third phase that is sitting here. If the machine is wound indeed like this, then what would happen is, around, if you start from one point and then go around and complete the circle, you would encounter exactly one cycle of variation of the MMF, which means that this MMF is going to generate a magnetic field that has one north pole and one south pole, and therefore this description whatever we have written is for a two pole machine. How does this description change if one were to consider a machine with more number of poles? If there are more number of poles, then in the same 360 degrees, of course, more poles has to be created, which means that these would then become shorter, and then you would have, for example, R phase and then a Y and then a B, and then again this R, Y and B. So, this completes one MMF from 0 degrees, it would come back to 360 degrees. This, from the start of this to the end of this, will be one cycle of the MMF waveform, and you want to have one more cycle of the MMF waveform. So, you would have R again and then Y again, then B and then R, Y and B. So, the stator has to be rewound or redesigned if you want more number of stator poles. But however, we know that whatever is going to happen between the start of one cycle of the MMF waveform and the end of one cycle of the MMF waveform, the same thing is going to happen this side also. There is no difference between what the machine is going to see here and what the machine is going to see here. Therefore, it may be sufficient if you analyze what is going to happen here, and then therefore it means that it is enough if you analyze one cycle of the MMF waveform. It is not necessary to look at the other similar repeats of the MMF waveform. Here you have the first cycle and here you are having the second cycle. If you are going to have more poles, then you need to shorten this, then you will have 1, 2, 3 and 4 pole structure, and so on. And therefore, since it is sufficient to look at one cycle or the space enclosed by one cycle of the MMF waveform, what we analyze is then a two pole equivalent, and the behavior will be the same. The only difference now is that an angle of 180 degrees is equivalent to 360 degrees of the MMF waveform, and therefore whatever angle we consider in these equations, if we now let that to be the electrical angle instead of the mechanical angle, the same description holds good for the induction machine having any number of separate poles. So one can have a 2-pole machine or a 4-pole machine or any number of poles. If it is 2-pole, then theta r is equal to theta mechanical. If it is 4-pole, then theta r is equal to 2 times theta mechanical. That can be seen from here. And if it is 6-pole, then the electrical angle is equal to 3 times theta mechanical. In general, the theta r electrical, which is what we are going to substitute in these expressions, can be written as the number of poles divided by 2 into the mechanical angle. So the induction machine description can then be written like this. What would happen to the expression for the generated electromagnetic torque? The generated electromagnetic torque, if it is going to be only a machine having 2 poles, you would get an expression like this, but if the number of poles increases, then what is going to happen in the second set of poles is going to add the forces generated on this side is going to add to the forces generated by the first pole pair, and therefore the torque generated would correspondingly double. If you are going to have one more pole pair, the torque generated would become 3 times, and therefore in general what is written is P by 2 times, where P is the total number of poles, P by 2 into this would then give you the total generated electromagnetic torque. So once this is known, then you can write the expression for the mechanical subsystem. Then the moment of inertia multiplied by J d, that is multiplied by d omega by dt, is then the generated torque minus whatever load torque is there. The load torque could again be dependent upon speed in some form. This expression then describes the behavior of the mechanical subsystem. Note that what we put as speed here is the actual speed of the machine, actual speed of the rotor, which we can call it as omega mechanical. If you take the derivative of this angle, this will then be, the derivative will be the electrical speed that differs from the mechanical speed by the number of pole pairs. So accordingly, if you now want to compute the angle from this, omega m is nothing but d theta mechanical by dt, and in order to substitute this angle into that, you need to multiply it by the number of pole pairs. So if one takes care to do that, then the description that we have now holds good for a machine with any number of poles. Appropriately it could be taken care. So this is the natural reference frame description for the induction machine. Now let us look at how the description will look like for a synchronous machine. So a synchronous machine description, and in this let us look at the salient pole synchronous machine. This is a more general case because here we are as we have seen in the earlier derivations of the MMF inductances and all that. The salient pole synchronous machine has a non-uniform air gap and hence is described by two inductances, one along the direct axis and quadrature axis called LD and LQ. If it is going to be a cylindrical rotor induction machine, then the air gap is uniform and we can simply arrive at that description from this by saying that LD is equal to LQ, and therefore let us look at the salient pole machine. The salient pole machine again has a stator and the rotor is salient pole. So, let us assume that the rotor is at this position and as before we assume that the A phase of the stator is here, the return conductors are here, and then the next phase of the stator comes here and the return conductors are here, and then the C phase of the stator, that is the blue phase, comes here and then its return conductors are here. So, this is the same description that we followed earlier. Now, the rotor has an angle, the rotor axis is situated there and that makes an angle theta r with respect to the stator A phase axis. So, this is theta r. Now, on the rotor let us assume that two sources of excitation are there, one which will generate an excitation along this axis, that is axis of the rotor, and another coil which generates an excitation along this axis which is 90 degrees to that of the rotor. So, with this system we need to now start writing the system equations, and we start as before, we did as in a similar manner to what we did for the induction machine. The starting point is always VAS is equal to RS into IAS plus P times psi AS. This is for the stator A phase, and similarly you get an expression for VBS RS into IBS plus P times psi BS, then VCS is RS into ICS plus P times psi CS. These are the three windings on the stator, and now you have two more windings on the rotor, which one generating an MMF along the pole phase axis, another generating an MMF perpendicular to the pole phase axis. We will call them as windings F1 and F2. So, Vf1 is then Rf1 multiplied by If1 plus P times psi F1, Vf2 is Rf2 times If2 plus P times psi F2. So, this is an equation set similar to what we wrote for the induction machine. Now, there are one or two points to note in the equations that we have written down. These equations assume that if you have a coil on the stator which is going to generate an MMF along the AS axis. So, let us say this is a coil on the stator, that is your AS axis and BS and CS. This means that there is a coil on the stator generating an MMF along the AS axis. The actual location of the coil would be, as we have seen earlier, displaced around the circumference. So, this expression VAS is valid for a voltage that is applied to this coil, plus minus having shown like this, and the flow of current considered into the terminal marked plus. And similarly, if you have a BS coil, the voltage is plus minus here and the current is flowing into the terminal marked plus, and the dot points of the coils are such that it is dot at both places where current is flowing in. Similarly, you have the C phase coil, current flowing in and plus minus this way. This convention holds good for the induction machine as well. Now, what this convention means is that we have assumed that the reference direction of current is one that flows into the terminal marked plus, and therefore the equations we have written down follow the motor convention. So, what we are developing essentially are equations for a synchronous motor in this case, and the equation that we have derived earlier is for an induction motor. So, both are for motors. Let us have that in mind, and if it is going to be a generator, what we are going to do is only say that current is flowing out, therefore the currents in the stator become negative if it is a generator. Let us not discuss more about that now. For the present, let us go ahead with developing these equations. So, the next thing, as we have done for the induction machine, is to write down expressions for the flux linkages. Let us start with psi AS. Psi AS is again going to have a self flux linkage, self flux part and a mutual flux part. The self flux part arises from the current flowing in itself, that is IAS, and the mutual flux part is due to the currents flowing everywhere else, that means IBS, ICS and the two currents in the rotor IF1 and IF2. So, how do we write down the expression for self flux? That is fairly easy. This is, as we have seen, the flux linkage is inductance multiplied by the flow of current, and for a geometry like this, which has a cylindrical stator and a salient pole rotor, we have already derived the expressions for the self inductance, and we know that the self inductance LAS, for example, is given by a leakage inductance plus LD plus LQ by 2 plus LD minus LQ by 2 into cos of 2 times theta r. This is an expression which we have derived earlier. So, the flux linkage arising due to that is this self inductance multiplied by the current IAS. We need to then look at the mutual flux, and let us consider the mutual flux arising between AS winding, mutual flux arising in AS winding due to the current flowing in BS winding. Again, we have derived the expression for the mutual inductance between two windings on the stator with their axis displaced by an angle delta, with the arrangement of salient pole machine, and we have found that that expression is LD into cos of theta r cos of delta minus theta r minus LQ into sin theta r into sin of delta minus theta r. This is again an expression that we have derived. So, let us try to simplify this expression. This can be written as LD into cos theta r multiplied by cos of delta minus theta r can be written as cos delta cos theta r plus sin delta sin theta r minus LQ into sin theta r multiplied by sin delta cos theta r minus cos delta sin theta r. So, expand this further. So, this gives us LD cos square theta cos delta theta r cos delta. Here you get LQ sin square theta r cos delta. So, this is one part, and then you have plus LD cos theta r sin theta r. Sin delta we can take this out, and then you have minus LQ sin theta r cos theta r multiplied by sin delta. So, this can be written as LD cos square theta r is 1 plus cos 2 theta r by 2 plus LQ into 1 minus cos 2 theta r by 2, this whole thing multiplied by cos delta in both places. So, that is cos delta, and then you have here it is cos theta r into sin theta r. So, that is sin 2 theta r. So, LD sin 2 theta r by 2 minus LQ sin 2 theta r by 2 multiplied by sin delta. So, let us look at this expression further. So, that expression can be further written as LD plus LQ by 2 plus LD minus LQ by 2 into cos 2 theta r multiplied by cos delta. Here you have cos delta, and then you have LD minus LQ by 2 into sin 2 theta r multiplied by sin delta. So, that becomes LD plus LQ by 2 cos delta plus LD minus LQ by 2 into cos 2 theta r cos delta plus sin 2 theta r sin delta, that is nothing but cos of delta minus 2 theta r. So, this is the expression that we get for the mutual inductance, and in the case of the synchronous machine, of a balanced synchronous machine, 3-phase synchronous machine, we know that delta is equal to 120 degrees between the A and B phases. So, if we call LAB as the mutual inductance between the A phase and the B phase of the stator, that can then be written as LD plus LQ by 2 into cos of 120 degrees is minus half. So, minus half plus LD minus LQ by 2 into cos of 2 theta r minus 2 pi by 3. Delta is 120 degrees and minus half. So, this can be written as minus 1 by 4 times this expression. So, this is between A and B. If we consider A and C, so let us write LAC then what happens is delta, which is the angular separation between the axis of the A phase and C phase, now becomes 240 degrees, and therefore you have LD plus LQ by 2 into cos of 240 degrees plus LD minus LQ by 2 into cos of 2 theta r minus 240. We can write it as 2 theta r minus 4 pi by 3. LAB we know must be the same as LBA as well, that means mutual inductance between B and A phase, that is A excited flux linkage in B, and similarly LAC must be the same as LCA as well. What remains is LBC. To find out LBC, we can use the same expressions, but we must understand how this what is the geometry for which this expression has been derived. We can see that by looking at this expression. Let us remove the rotor for the time being. We are looking at the stator flux linkages. So if you remember, what we have done to derive this expression for the mutual flux linkage is that we have considered that a winding is there along the axis 1, and then the rotor is situated at an angle theta r with respect to the first winding, and a second winding is located whose axis is located as an angle at an angle of delta. This was the geometry for which we had derived the expression for mutual inductance. Now this figure as such can be used to determine the expression for the mutual inductance between this A phase and that of the B phase. The rotor makes an angle theta r with respect to that of the A phase. The C phase on the other hand is here, this is BS and this is CS. We now want to derive an expression for mutual inductance between B and C. Now that would mean that if you want to use the same expressions what we have derived, those expressions stipulated that the rotor angle that is considered is the angle made between the axis of the first coil and that of the rotor. Now the first coil is BS and the rotor is sitting here, and therefore the angle we need to consider is now this angle, and the separation between the two axes is still the same delta 120 degrees, and therefore the expression for mutual inductance would arise from whatever we have derived if we substitute instead of theta r this angle, and that angle is nothing but 2 pi by 3 minus theta r, but the rotor is now on the other side of the axis, and therefore this is a negative angle. So if we substitute instead of theta r this expression, we should get the expression for mutual inductance between the B and C phases, and therefore this can be written as LD plus LQ by 2 into cos of 120 degrees, delta is still 120 degrees, plus LD minus LQ by 2 into cos of delta. Instead of theta r we are going to substitute that, therefore minus 2 times 2 pi by 3 minus theta r, and because that is negative this now becomes plus, and therefore the second part of the term becomes LD minus LQ by 2 into cos of 2 pi by 3 plus 4 pi by 3 minus 2 theta r. So this is simply LD plus LD minus LQ by 2 into cos of 2 theta r. This term remains as it is, and cos of 120 is again minus half, therefore you get minus of LD plus LQ by 4 plus LD minus LQ by 2 into cos 2 theta r. So with this then we have derived expressions for the mutual flux linkage. What you would have in the psi as expression then is psi as is then LAS into IAS plus LBS into IBS, LAB into IBS plus LAC into ICS. LAS is the expression for mutual inductance that we have derived, self inductance that we have derived here. LBS, LAB is the expression for mutual inductance we have derived here, LAC we have derived here, and then there are two more terms, one that would describe the mutual inductance between that of the A phase coil and the coil acting along the axis of the rotor, that can be described as a maximum value of mutual inductance. We will call it as MAF1. If these two axes are aligned, then the mutual inductance of those two coils would become the highest, and as it goes out the mutual inductance will change as cos of theta r multiplied by the current flowing here, which is that of IF1, and then the mutual inductance between this winding and the winding which lies at an axis 90 degrees to that of theta r on the rotor. So if we call that as MAF2, then that is cos of theta r plus pi by 2 into IF2. Cos of theta r plus pi by 2 is minus sin theta r, so we can write it as minus sin theta r into IF2. So this would then be the expression for the flux linkage of the A phase in the stator. The flux linkage for the B phase can be written as LAB into IAS plus LBS into IBS, LBS being the self inductance of the B phase winding, which will have the same form as that of LAS, except that theta r will have to be replaced by a suitable angle, and then you will have LBC times ICS. The expression for LBC again we have derived, which is of this nature, and then you have a mutual inductance between the B phase of the stator and that of the rotor, that would then again be MAF1. Had the rotor been aligned with that of the B phase axis, the inductance would have been maximum, and since the A phase coil, stator and the B phase winding of the stator are not really different in the number of turns, the maximum value of mutual inductance would still remain the same, and therefore this is still the same MAF1 multiplied by cos of theta r minus 2 pi by 3 times IF1, and then you would have MAF2 multiplied by MAF2 would be the mutual inductance between the B phase and the coil here, this angle being 90 degrees, and therefore that would be cos of theta r minus 2 pi by 3 that is this angle minus 90 degrees. So, minus pi by 2 times IF2, that can further be simplified. And similarly one can write the expression for psi Cs as well. I will leave it to you as an exercise to derive the expression for psi Cs. For the rotor, psi F1, if we write, the flux linkage in the rotor would again have a self flux component and a mutual flux component. The self flux component can be written as a leakage inductance of the F1 coil plus the magnetizing inductance of the F1 coil multiplied by IF1, and then you have mutual flux components. Now if you consider mutual fluxes, there are 3 coils on the stator and one more winding on the rotor as well, but the rotor winding, it has an axis 90 degrees with respect to that, displaced by 90 degrees with respect to that of F1, and therefore the mutual flux arising due to that on the F1 coil will be 0. The stator being cylindrical, the mutual flux linkage between these two is 0, and therefore 0 multiplied by IF2. And then you have the mutual flux linkages between the stator windings and F1, and those are described by the same mutual inductances that we have written here, whether it is between stator flux linkage caused due to current in the rotor or rotor flux linkage caused due to current in the stator, the mutual inductance term remains the same. Therefore similar mutual inductance terms would then arise. If we look at the flux linkage in the coil, the second coil of the rotor, you would have no flux linkage due to current in the first coil on the rotor, but there would be a self flux linkage component. There would be self flux linkage component, which is IF2, and then you would have mutual flux linkage components, similar terms arising due to IAS, IBS and ICS. So having written all this, one can now complete the expression for the electrical subsystem description of the synchronous motor. Once we write this, then the expression for the generated electromagnetic torque again can be written as half of I transpose dl by d theta r multiplied by I for a 2-pole machine, and if you are going to have more number of poles, that can be multiplied by the number of poles there. So it is p by 2 times this expression. This equation, again these set of equations, as for the induction machine, they are said to be in the so called natural reference frame, because the variables are as they would be in a real life induction machine, naturally found variables. So it is called as natural reference frame. What we see from these two descriptions is that the description of the induction machine and the synchronous machine is fairly elaborate. You have a large number of system variables, the description is quite huge, and the expression for the generated electromagnetic torque would also be an unwieldy expression consisting of many variables that are in that expression. Therefore we look at some ways to simplify this expression in order to make handling these expressions easier, in order to make solving these expressions easier. One looks at a different way, a different approach to solving these set of equations. What is that? We shall see in the next lectures to come. For this lecture we will stop